This video is brought to you by Hackeramo Chalk. Use code TPSA 10% off to get a discount.
Welcome back. In today's lecture, we're going to be talking about the derivative on curved spaces, introducing the covariant derivative, as well as talking about the Christoffel symbols. So, from what we've built up so far, we want to now talk about a derivative in line with the principles of general relativity that we've outlined so far. Them being that this derivative should be coordinate independent and should so we can gather that it's going to involve something that transforms like a tensor, so that it satisfies the principle of general covariance. Okay, so if we want to do this, we can stick with our index notation so far if we define the following. So this kind of partial with a lower mu, we're going to define to be partial derivative with respect to x mu. So this then kind of makes it like a vector. I have a lower index because if I was to make a coordinate transformation from x mu to y mu by the chain rule, which we discussed in the previous lectures, this would go to the x mu, partial y mu, partial mu, which is just exactly how a covariant vector transforms. Okay, so that's kind of our partial mu prime. Okay, so this kind of index notation and it transforming like this kind of gives us the illusion that this will be perfectly valid as a tensor-like quantity or tensor quantity, rank 1 tensor, or rank 0, 1 tensor. So, but we will actually find out that this is not the case. So, for example, if we were to act this on the sum vector or the components of a vector v, and we were to take the partial derivative, now notice I have the same index here, which means I'm summing over. So let's say we had four components, then this would just look like a kind of like divergence, which you may have seen from vector calculus. 2v2 plus v3. Okay, so that's kind of what we get from that. But then we can check something. Let's look at this quantity. We can actually make this arbitrary. So let's just say it wasn't the same component. Now, what would happen under this coordinate transformation up here? Well, we know that the first one would behave like that. We get a partial x mu, partial y. Let's go for alpha now, out the front. And then we get the partial mu here. Hold on, there's too many indices here. Sorry, that should be a mu. Let's kind of have more than 2 indices. Okay, so we'll call these. Okay, and then on the inside, we know that our vectors transform the other way. So it's going to get a y up top and an x will stay same on the bottom. Hold on, let me just figure this out. So b alpha, or we call this one beta. Okay, that's how that's going to transform. So now we're going to run into an issue. Okay, let's do out the product rule here on these two terms in here. So the front term will stay the same. We're going to get, so first it's going to act on this term, or let's first act on this one. So we're still, this term gets unchanged by the derivative, and then you get b alpha, b beta. That looks like a good term, right? We had an upper and lower index, and it's transforming, and we're getting two of these terms at the front. That's exactly how a tensor transforms. That's looking good. But this second term is also going to get hit by this derivative. So we're still going to have this front term. We're going to have v beta, and then we're going to have our, we'll put that at the end. So this is going to hit this. Now this is just like a second derivative with respect to x. So it's d squared y. Then there's 1 dx alpha for the index alpha. That's just this one using that definition. And then there's 1 for the dx beta. Okay? And then this doesn't get hit by this derivative here. So we have seen that this quantity, or coordinate transformation, has given us a term that looks exactly like a tensor with the bits at the front and something extra, which is not a tensor. So this completely ruins this guy's chance of being a tensor because it does not transform like one. So this is a little annoying for us in general relativity, as we want something that transforms like a tensor. That's what we want to build our theory out of. So this isn't really something that people encounter when looking at something like special relativity. And the reason for that, I want to just outline, is if you look at this, it's a second derivative of the coordinate transformation. So we change from x to y, and we have a second derivative. But in special relativity, our coordinate transformation, we do Lorentz transformation, which puts this kind of Lorentz matrix, which we had in the one of the previous videos, the second one. Now, you may remember that this matrix looks like, just has a gamma minus gamma beta over c minus gamma beta over c, gamma, and so on. So it's constructed of gammas and betas, which is just, or not beta, it's b over c, or v over c, not beta. Beta is defined as v over c sometimes. Okay, so it's just dependent, and gamma is the Lorentz factor, which is only dependent on the velocity. So if you were to take two derivatives of this, the first one would knock off that x. The second one would be acting on something which is not dependent on the coordinates. So this term would vanish under any Lorentz if this change of coordinates was a Lorentz transformation. So nicely in special relativity, this is preserved as this transforms like a tensor under the same transformations we use in special relativity. So that's quite nice. But for us in general relativity, we're going to need something different. Okay, so as we have outlined, we're going to need a new sort of derivative that's that we want to form when we take the derivative of tensors, that we get back something that is also a tensor. So we're going to need to figure out how to get that. Okay, so when it comes to the derivative, there are two rules that we simply can't do without. Okay, so there's not the Leibniz's rule. So we're going to denote our covariant derivative with a nabla. If we take the covariant derivative of, say, two vectors, I'm just going to ignore any indices for now, that doesn't matter right now. We take the covariant derivative of any two vectors or tensors, then we expect that this will obey the Leibniz rule, the product rule, in that we will get nabla u by v plus u nabla v. Okay? We also have linearity. Okay? So if I take the covariant of the linear combination of two vectors, well, where alpha and beta are constants, then the constants, obviously, as they do in differentiation, shouldn't matter, and this should just expand as follows. Okay, so that's pretty good. So these two make this covariant derivative operator a linear operator. So we'll call that 1, 2. We're going to need two more things if we want it to be covariant. So remember, we saw so far that we took the partial derivative of our vector, but when that transformed, we got this extra bit, which made it not a tensor. Now, if we were to have just, let's say, a scalar, phi, and we take the derivative of that, well, if it's a scalar, by definition, when it transforms, you don't get anything at the front. So we must have that when we take the covariant derivative of a scalar, well, this should just be the same as the partial derivative of that scalar. So that's a condition we're going to impose when we try to come up with a covariant derivative. The fourth one is very similar. So let's say I take the covariant derivative of a tensor, and it has some contrasting indices. So there's one upper and one lower. Then when I do this, these, if they were to transform, will give me 2 bits that cancel, as we've seen in the previous lectures. So these should commute with the covariant derivative. What I mean by that is when we take this outside, oh, sorry, repeating indices that shouldn't. This should be the same quantity. That so when I can take them out of this covariant derivative, such as this, like acting in on this, and that shouldn't make a difference in my calculation. Okay, so with these, it turns out we can figure out a lot. So the first thing will be figure out how this looks when it acts on vectors, right? So scalars, we've obviously pretty much already by definition defined it that way, and we saw already that using this definition for vectors doesn't work. It's not a tensor. Okay, so let's go figure it out. So we know that, okay, whenever you're dealing with vectors, I need to reiterate once more that when I say we're dealing with vectors, what we are really doing is dealing with these quantities v, which are the sum of some components, so these are just numbers, over some basis vectors, b. So here the index, each mu v is a number, but for each index here, v is a vector. So there's a difference between these. And whenever we're going and are doing stuff like this in GeoR, we are often dealing with these quantities with respect to no coordinate system. It's just that the b mu's are we always ignore them as they're not that relevant, but they'll be very relevant here. Okay, so the problem when we get to curved spacetimes, which is where this covariant derivative becomes prevalent, is that the basis vectors no longer a constant throughout our space. So we are used to having, let's say we have our Cartesian coordinate system. We have our 3 basis vectors. No matter where you go, they're always the same length. They're always the same. So you would have that, like your covariant derivative of your basis vectors just your regular derivative is always 0. But that's not going to be the case. In our covariant derivative, in our curved space, as we go around, our vectors are inherently going to change length. They're going to change length, going to change direction, move. So this is not going to be the same. Okay, so how is it going to change? So to do this, we're going to go back to like how we originally find a derivative. We're going to get 2 points, see what changes between them with like some function, and then infinitesimally take those points together. And that usually gets us what we want. Okay, so let's say I have a point P, I have a point 3 prime. Okay, at here, I can expand my basis in B mu, and at this point, they're going to change to B mu prime. Okay, because you go along and they're going to change. Okay, so great thing. So if I was to just look at the vector space here and look at the vector space here, then what I can always notice is that I can always find some matrix transformation that allows me to write my a new basis in terms of the old one, right? Now, if this P and P prime, so if P equals P prime, then these would just be the same. So that would imply that the C mu, the C matrix is just the identity matrix, right? Then they would just be the same. Okay, that's not too bad. Now let's consider if they're just very close together, but still a little bit apart. So P is not equal to P prime. But okay, they're really close. So C is going to look like this plus another small bit, right? So this C matrix is going to look like the original plus some epsilon times some matrix, okay? And it's going to have some other bit like that, okay? It's close enough. Okay. Then how would we go about defining derivative? So if we were to take our covariant derivative of our basis vectors, then this would be, well, the limit as epsilon goes to 0 of b prime mu minus the original b mu all over epsilon. Okay. Well, then we can sub in what we have above. So that's the limit as epsilon goes to 0. Then this is just this one here. It's the different one. Plus epsilon nu mu. And then this one is going to be the same as that. Sorry, but there's a minus in front. There's a minus there. That's all times b nu over epsilon. So what we can see is these deltas are cancelled. These epsilons will cancel. And we're just left with that little bit of a matrix there. This capital gamma I've used. Okay, so that's pretty cool. But notice one thing I've done here, I haven't had an index here. So I've just taken a derivative along one direction, but this occurs for every direction. So what we really should have is that for every direction, let's say rho, the derivative along b mu will give us some symbols by rho, which are in the form of a matrix, times b mu. The b mu there. Okay, then what we end up doing in GR is we take this symbol and we define it to be just one gamma with an upper nu and two lower indices like that. We kind of forget about the distinction between them because it's not that useful. So these quantities will be very important as we go along. But now that we figured out how the basis vectors transform, we can go ahead and figure out, well, how do vectors overall transform? All right. So we'll just write this out. All right. So let's take covariant derivative with respect to an index here of a vector v. Now, as I said before, this is the covariant derivative along some direction with respect to v mu and b mu. Okay? And we're going to apply the Leibniz rule because there's two bits here. Okay? So first we'll act on this bit and b mu, and then we'll act on the other bit. So we'll write v mu first, covariant derivative rho b mu. Okay, now we have to do something kind of funky with this bit here. Because I'm splitting it up like this bit is specifically only the components. Now these components are just functions, so they are only scalars. So this will reduce to just the partial derivative along here, okay? Which is quite nice. The other bits, we can use our previous rule. Down here, we're going to get v mu, and then we're going to get these symbols, okay? It has three indices, but I'm not going to call it a tensor because it turns out this thing doesn't transform like a tensor. Okay, so if I've done that right, that looks like so. Now what we can do is we can relabel some indices. So these are nus and contracting, these are mus and contracting. So what I can do is I can call these nus and then I can call these mus. Doesn't matter what label I did. But what that does is it allows us to write this. V nu gamma which is going to be a mu now, because I swapped the labels. That's a nu now. And then that just allows me to factor out the v nu. Okay, so we've taken the derivative of a vector, and we've gotten a thing with a basis. So this thing here must be the components, the new components of the covariant derivative. So that's how the covariant derivative is going to transform. And that kind of makes sense. Remember we had, when we did it this way, we got this thing back plus some extra term. So basically what this thing is doing is this will counteract the extra term that comes out of this. That'll cancel and give us back the original thing. Right, that's pretty good. Now I have to break some bad news. So index notation so far has been really, really useful for us. But there's some situations around here where it really starts to actually just be a nuisance. So many people take this quantity and they'll denote it, they'll forget about those brackets, and they'll just write this. But then that gets really confusing because I already told you this is a scalar. So many people actually ignore this altogether, and they'll write this as v nu, and then they'll write a semicolon with a row. Sometimes that's how they like to write it. But for the sake of convenience, I'm also going to use this. But it's whenever I write this, I really mean it's the components of the derivative of the vector. It's just unfortunate that it all kind of gets confusing like this. Okay, so that's how covector transform, the ones with the upper indices. Let's now see if we can figure out how do lower ones transform, ones with lower indices. That might not be the same. So to use this, we can use a neat trick. Right? I have said my rule 3 was that if I take the partial derivative of the scalar, or no, a covariant derivative of the scalar, it reduces the partial derivative. So let's say I take the covariant derivative of, go back to row, of combination. So I have a vector, as we did before, but I'm dotting it with a vector with lower index. We showed in the last lecture, I believe, that this transforms like a scalar. So this, so first I'm going to expand it. This is going to be expanded with the Leibniz rule. So we're going to get a something like this, plus the other way, rho mu mu, okay? But remember I said that this is a scalar, so this should also be equal to the partial derivative of v mu u mu, which will also obey the Leibniz rule, so we can also expand this as so. Okay, we'll see where I'm going with this in a second. Let me write all this out. Rho mu mu. Okay, so this is the thing I want. I want to know how the covariant derivative acts on a lower index. Okay, so I'm kind of just going to mess around with things and solve for this. Okay, so this we can use our regular covariant derivative that we did earlier. So this is going to give me the partial derivative of v mu plus my, so it's going to be plus a v nu, v, the operator, mu and a row, and then the lower is mu. Okay, that's good. That gives us that. That looks good index-wise, yeah. Plus this term still, so v mu u mu. Okay, and that's equal to that right side over there. Okay, so I'm just going to boop, 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 boop. That's the same. Okay, then I want to move everything to the other side to get rid of this thing. But what we can actually see is this term here. Let me write it as. We can see that partial rho v mu u mu plus v mu partial rho u mu. Okay, Well, this term is actually the same as this term. You see all the indices and things match up. So we can cancel those. And then all we have to do is move this term over to the other side. So then we get that v mu nabla rho u mu is equal to this term v mu. And if we have a v mu here as well, which is good, so we can factor them out. So nabla rho u mu. But when we move this over, or no, sorry, this one. Well, we can relabel the nus and mus in this one as well. But when we move it over, it's going to pick up a minus sign. Now we're going to get a u, which we rename to nu. So I'll swap this again, so this mu becomes a nu, a rho, and this becomes a v. Okay. So that's going to look like that. Okay, that looks pretty good. So we must have this thing here, because I have v nu on both sides. I can just cancel. So this thing must be equal to that thing there. Looks very similar. It's almost the same, except we picked up a minus instead. So that's kind of happens with the covariant derivative, is on upper indices it's going to give us a plus, and the lower it's going to give us a minus. So you can do similar arguments for where you take the covariant derivative of the tensor for of any combination of tensors like this, and you can repeat the same arguments, and you're going to get basically a long list. The ones with uppers will be will give you positive plus the symbol, gamma symbol, and the ones with lower and any lower index will give you a minus with that. So overall, it's gonna look like this, which is quite a mess. Okay, so let's talk a little bit more about these strange symbols, which I denoted the capital gamma, like this. Okay, so the four conditions we have so far in our covariant derivative are actually not enough to determine these uniquely. Still have left over. So we can perform some kind of, you can think of it kind of like a gauge fixing in like we do in electromagnetism. We're going to impose some other conditions on this so that we can determine them. So the first one is I'm going to impose that if I swap these two indices, that I get the same thing. Okay, so that it's symmetric in these lower two indices. This is known as torsion-free condition, because while these two things I've said before are not a tensor, you can actually find that the difference between them is a tensor. So if I was to take this tensor here minus this is a tensor. But what we're going to do is I'm going to set this to 0. This is basically a thing in Euro. There are other theories of gravity where this is actually non-zero and has a role to play. But for us, this difference will always be 0, and we can always make identification. So this is condition 5 for our covariant derivative. Okay, and then we're going to do one more. So this is condition 6, and it's called metric or compatibility. Okay, so this is going to say that if I take the covariant derivative of my metric, I want that always to be 0. This is very, very handy because you can think of if I have tensors and indices inside my covariant derivative, I want to be able to bring in my metric, raise, lower them, and it's very handy like that. We're also, later on, going to find a very nice physical condition that kind of ties in with this to justify us making that claim. Okay, so I'm going to, now, as I said, with these added conditions, I'm going to just stick this up in the corner. This will be enough to determine our covariant derivative. So let's go, or not covariant, our Christoffel symbols, which in turn give us our covariant derivative. Let's go see if we can find this. So if this is true, well, it actually will also be true. I can flip these indices around. Now I need to make this cyclic because the metric tensor is symmetric. So swapping these doesn't do anything. So I need to kind of shuffle them along. So let me first bring the mu over and then slide these over so that I get a nu and a rho. So that's going to be 0. And the last one will just be like this. That's also going to be equal to 0. So these are kind of 3 things that I can use to solve. So then we're going to use our definition of how the covariant derivative acts on tensors, which I wrote down not so long ago, and we're going to see if we can solve these. So remember I said, so there's 2 lower indices. So this is going to be, let me just write, is equal to, so we're going to get, first of all, we always get the partial derivative of the thing itself. Now, because there's lower indices, we're going to get minus. Then we get back the thing itself. Or no, sorry, we get the Christoffel symbols first is easiest. So in this case, it's going to be the top bit that's summed over. It's going to be a rho. And in this case, we'll first pick the mu to sum over. So that means the sigma replaces the mu here, and the mu goes there. Here might have been, if you ever have like an ambiguity here, do I pick the mu or the nu first? There's an ambiguity there because both of those terms exist in kind of equal capacity. So I can do the same thing here, and this time I take the mu. So now I'm going to g, and the sigma takes the place of the nu. Okay, so then we have to write this for the 3 other terms. Let me just do that real quick. So this time, sorry, it's not going to be that. It's going to be a mu. We're getting a g and a nu rho. Okay, then it's minus sigma at the top. The mu goes here. We're going to be taking out the nu first. So sigma, and then this is going to be the rho minus sigma. This is mu again, and now it's the opposite component. So this is going to be rho. This is going to be g, and this is going to be nu sigma. Okay, then last one, g with respect to nu is the derivative now. So that's going to be rho mu minus sigma top. Now this is going to be our nu. Then the first component is rho, gets taken out for the sigma, and we're left with a mu. And lastly, sigma top, nu, mu, g, rho, sigma. Okay. Then, so 3 equations. 1, 2, 3. What I'm going to do, oh boy, is I'm going to add the first 2 together, and I'm going to take away the third. Let's see what this looks like. That will give us plenty of boardroom. Okay, so add the first 2. Let's just look at the partial derivatives. Mu plus the second term, which is g mu or g nu rho minus the third equation. So this one's going to get a minus g rho mu. Okay, now I said I was adding the first equation. So that's going to give me sigma rho mu g sigma nu minus gamma sigma rho nu g mu sigma. And then I'm adding the second equation, so we'll go through that. You'll see we'll make a lot of cancellations here. It's not going to be this messy forever. G sigma rho minus gamma sigma mu rho g mu sigma. Okay, let's stop before we add. Let's add them in. So then there's just these last terms, which are getting minuses, so the minuses are going to cancel. Gamma sigma nu rho g sigma nu plus gamma sigma nu mu g rho sigma. Okay. Phew. Okay. Now let's look at some terms. So here we have a rho and a mu. And we look around our board. and we see if we can see any other term like that. And I see a rho and a mu here. And because the metric is symmetric, I can swap those two. So you can see those two terms are the same, but they also have the same sign. So they're going to add together. So sorry, I'm just going to write out this bit. So minus sigma rho mu. So there was two of them. They both have minuses in front. So there's two of them. G sigma nu. That's fine. This next term has a rho and a nu. And here I see also a rho and a nu, but it has an opposite sign. So these two are going to cancel. Okay. Then we have a mu and a nu. And we have a mu and a nu. They're opposite sign again. So these two are going to cancel. And then this one and this one are just what I combined to give there. Okay? So that's just 0. That was our condition. So if I add these two, all these equations are 0. So any combination like this will also be 0. Okay, we're almost there. Let me just take this term and move it to the other side because it's minus, and then we'll be left with that term. So 2 gamma sigma rho mu, G sigma nu is equal to, and just the terms and all the partial derivatives in that order. G mu nu. So you can see I added these equations in a very suggestive way that nicely cancels stuff. It's a lot harder to figure that out by looking at them. Okay, so now we just have to isolate these symbols. So we can obviously divide by the 2 to get a half. Now to get this G across, we can use the fact that G, let's say mu nu, G nu alpha. This, by definition, this is the G inverse, the inverse of the metric. So this thing is equal to the identity matrix with indices alpha and mu, as there are only 3 indices. Okay, so if I apply across the matrix, let's apply across with G. Let's go with nu beta, alpha, nu alpha to both sides. Then I'm going to get that when this applies to the G sigma nu that I have here, well, I'm going to get G or delta sigma alpha. That's what that's going to give me. So if I apply that across, I'll get my delta sigma alpha, and then a half. So I applied the G nu alpha, what I applied across. And I've just got to squeeze in all these partial derivatives here. G mu nu plus partial mu G nu rho minus G nu G rho mu. Okay. And then the alpha, this just identity matrix just means alpha must be sigma. So that means that we get an alpha up there, a mu is equal to this thing here. Okay, so ignore my sloppy presentation. There is our Christoffel symbols. Okay, so we can see that we can completely express them in terms of first derivatives of the metric, basically. So very, very messy, but you can, now, the very annoying thing about these things is they are not tensors, and when things are not tensors, they're not coordinate independent. So for any coordinate system you want to use, you got to calculate all of these symbols. Now think of them, if you have 4 dimensions, that's a 4 times 4 times 4. 4 to the power 3 is like a big number. Like 64 plus 64, 4 plus 64 plus 64. Annoying number. So, no, it's not. Don't worry about that. So there's a lot of these symbols, and you have to calculate a lot of them for each coordinate system you do. You can't like calculate them in one coordinate system that's nice and transform them across because they're not tensors. So that's yet another reason to why we use tensors. But these will be very useful if we want to take any covariant derivatives, which we'll see more of later. Okay, one last thing to mention is that, so we know when we take the covariant derivative, we get the partial derivative plus something that's proportional to these Christoffel symbols. So we would expect that when we go to flat space, that these would vanish. And that's indeed what we see. If we think of our metric, if it's just a flat space metric, then it's just a constant, and all of these derivatives will just vanish, and we get our zero symbols. So I've been calling them, so far you may refer to them as Christoffel symbols. These are known as Christoffel symbols, or the Christoffel connection. They're known as the connection because we saw earlier that the covariant derivative of our basis vectors gives us the Christoffel symbols times like the multiplying our new the basis. Okay. So what this does is it tells us how. So before, and when we have arbitrarily curved spacetime, we cannot compare vectors at two different points. But what the connection does is it tells us how we can compare vectors at infinitesimally close points. So it gives us a connection for how we can compare different things at different points.